Ruediger Urbanke, who received his PhD from the University of Washington at St. Louis, and then worked at Bell Labs, and then moved to EPFL in Lausanne, where he has been for 11 years, I think. He is one of the leaders of modern coding theory. He, with Tom Richardson, did the fundamental contributions, density evolution, the whole theory to rigorously analyze, and wrote the Bible in that area. Not so easy book to read, but for that topic. He recently received the Koji Kobayashi Award, and every year at San Diego, is that official? You do does in creative ways the Relief, which is a creative and innovative event. And without any further ado,
thank you very much, Alex, for your kind words. My mom doesn't believe anything, so definitely wouldn't believe this. So now I wanted to start, like all the other previous speakers, to thank the organizers, in particular Gerhard. It has been a fantastic and enjoyable event, and I hope it will stay so for at least 2 more hours. Now today when he came in, I saw that he had an even bigger smile on his face. I guess he must be very relieved that things will be over soon, and that so far everything went very well. Now I also should thank Alex, not just for the introduction, but also for this beautiful t-shirt. Okay, so the only reason I'm not wearing it is because I'm soon be on a plane. And since we heard yesterday that even simple information theory t-shirts can cause quite some social unrest, I didn't want to put the stability of the airplane and the passengers at risk by wearing this fantastic design. Now, Gerhard told us that if we had any complaints, we should complain to you. I looked carefully, but this formula is just so gorgeous. It's really nothing I can complain about. So thanks a lot. Now, when Gerhard asked some weeks ago, and he ever so politely but firmly reminded me for the third time that he needed perhaps a title. I was somehow desperate trying to look for a title, so I went on the webpage, and fortunately Sergey already had posted his title, so I thought I can't go wrong by following a Shannon Award winner, and so I simply stole his title. Well, I stole half of his title, let's say, and shamelessly stole it, and actually had an even much more devious plan, which unfortunately didn't quite work out. I tried to convince all the other speakers to follow suit too. So there would have been obvious choices. We could have had storing Shannon, okay. We could have had networking Shannon, okay. We could have had completing Shannon, okay. We could have had the obvious compressing Shannon, okay. And the only pleasure that we actually had was reading Shannon, okay. So unfortunately, I went into partial negotiations. At first looked like hopeful, but at the end the plan fell through, and so I was the only one that actually followed up. Now I was somewhat afraid, of course, that this being a Sunday, it's beautiful sun outside, and that this would be somehow like the tree falling in the deep forest. Okay, if you give a talk and nobody's in the audience, do you actually give a talk? But so I'm very happy and thankful that so many of you actually came out here and spent your perfectly otherwise Sunday in this lecture here. Now, it's particularly hard to be, or it's in general hard to give a talk or to give the 6th talk in a series like this. And after several days, of course, fatigue sets in. It's, of course, impossible task to do so if the previous speakers are Jack Wolf, Andrea Goldsmith, Emmanuel Candes, Alon Orlitsky, and Sergey Verdu. So I thought hard what I could possibly offer you. I'm afraid I didn't really come up with anything. The only thing perhaps I can promise you for this lecture, okay, since it's Sunday, exceptionally there will be no homework. Okay, so no homework today. You're lucky. Now, okay, so having set expectations sufficiently low, let me try now to start. So what do I want to do? Well, not surprisingly, I will, given the talk title, I will talk somewhat about coding. But what I want to do is, I would like to somehow try to maybe organize and compare things a little bit. And I want to do this from one particular perspective. So now, of course, given that we have only 2 hours, there's no way I can go, and it probably wouldn't even be useful, go through all possible coding schemes there are. So we'll limit ourselves to some, very few of them. I do everything in the simplest case, everything binary, only look at some particular constructions, leave out things like meta constructions, like concatenated codes, etc. So many, many things will be left out. But what I would like to do is particularly, 2 of the topics I'll spend a little bit more is iterative and polar coding. And I want to do the comparison in a particular way. And this was also alluded to already yesterday by Sergio. I want to look at a little bit at the finite length performance. And in particular, I want to look at an approach which is called a scaling approach, something that, in physics, this is a very, very standard approach. I don't know, probably 100 years or more old. In our community, you also find some traces going back to the 60s and so on, but I don't think it has probably been quite as much exploited as it could be. And I think it's a very useful approach. It's also, I think there's also a lot of open promise. You will see that there's only very few things we can rigorously state. Many other things we can conjecture. We can say that we think it behaves like this, but given all the brain power here, and if you're looking for problems, perhaps this one or the other of you might be interested in following it up. Okay, so now I don't think I have to give much motivation why we're looking at coding. Jacques has, sorry, I always say Jacques because, okay, I'm now in a French-speaking country. So Jacques has told us that, just for example, IBM alone, it was worth looking at constraint coding and also general error correcting code, a few billion here or there. And there's certainly many, many other applications. So it's certainly one area where theory meets practice and where any progress can actually make a difference. Now, just a disclaimer, what I will do is I will not put the reference directly on the slides, but I have after every section a list of references. And you should consider that these slides essentially are a summary or just an attempt of a summary of the papers that are always listed below. OK, so what will I talk about? I'll look at 4 very simple classes. I'll look at block codes. I'll look a little bit about convolutional codes. These 2 things we'll do fairly quickly. And then I look a little bit more in detail about sparse graph codes. And I look at polar codes. And so the question is, how will we, what exactly will we be looking at? Well, there are the obvious parameters that are of interest. There is a channel. It has a capacity, or maybe there's a family of channels that have capacity or parameter, maybe the epsilon or the sigma squared. There's a rate. There's the block length. And then the most important parameter typically that you deal with will be the error probability bit or block. Typically, I look at block. And then there's, of course, also complexity that plays a role here. And so what we're interested in is essentially which of these sets of parameters are possible, feasible, how do things scale. Now, traditionally, one of the main objects that people have studied are things like error exponents. And I will mention a little bit about it. So, which is you look essentially at this error probability here, and you're looking at a family of increasing codes, and you're looking at how the error probability scales. You're looking at the exponent of how the error probability goes down. And this can be in many senses. This could be either you're looking at an ensemble average, you're looking at the best code. So I didn't write down exactly. So either you have an expected value, you have maybe a supremum over all codes in there, but essentially looking at the exponent. Now, what I want to look at is at a slightly different limit. So let me explain exactly what limit I want to look at. So let's assume you have a family of channels, Gaussian channel. And then, so typically, you would have one axis in which you have the channel quality. Maybe you think of the epsilon, you're thinking of the sigma squared, the epsilon of an erasure channel. And then you would have your object of interest, let's say the error probability, let's say block as a function of n, the rate that you're transmitting, and the epsilon is, let's say, the channel parameter. And then typically, when you now plot for families of such codes, the performance, you would get these waterfall curves here. OK, and so we are interested in somehow trying to see if there's a little bit more structure in these curves than rather just having for every n and every r and every epsilon some particular value here. OK, now what happens? Well, typically, as you let n increase, the block length increase, very often in many systems, this performance will become, or these performance curves will become steeper and steeper. And in the limit, as you let n go to infinity, there will be some threshold behavior. Okay, so there will be some parameter, let's say a channel parameter here, and the curves in the limit will, the block error curves will converge to this step function here. And what I'm interested in is a scaling is somehow to investigate how, so one is the limiting behavior, let's assume we have, is how exactly these curves approach to this limiting behavior. Okay, so the way to do it is that you somehow first shift the axis, so first plot it as the difference between the asymptotic threshold and the channel parameter. So this will be now the driving parameter that we're looking at. And then statistical physics tells us that we should rescale this with some function of the block length. And so if you pick here n, at first, if you pick 1 over mu, so there's a parameter mu, it's typically for historical reason written as 1 over mu. If you pick 1 over mu to be 0, then nothing changes. The picture is exactly the same. But let's assume now that you let 1 over mu increase. Then what you typically might observe is that these curves will somehow become closer and closer. And if you're lucky, and if such a scaling actually occurs, then up to higher order effects, I'm not claiming that this is exact for finite length, but up to higher effects that will vanish, and we'll see in exactly what sense, for a particular mu, which is called the scaling, the particular scaling parameter, all these curves will actually collapse. Okay? And so then what we will call is mu, 1 over mu, or mu we'll call the scaling exponent, and we'll call the f of z here, so this curve here, we call this either the scaling function or the mother function. Okay? So in this sense that this scaling is correct, all these curves, all these billions and millions of curves that you see in traditional, whatever, if this is now coding or if this is a communications paper, you would always see these waterfall curves. In this sense, all these curves would be somehow the same curve. They would be rescaled versions of the same curve. Now, you might wonder why we exactly did this here. There's, this has a long, long history in statistical physics. And there are some very fundamental reasons which are, I don't think there's actually a proof of it, but there's some fundamental intuition. Why, for example, we used here n to some power, right? Why didn't we use log or square or some other function, maybe perhaps of n, okay? So in physics, people have figured out that there are certain universal rules that this is a certain universal type of scaling that applies to essentially all the physics problems that are known. I'm sure there's some exceptions, but this is kind of the fundamental type of scaling that happens. Now, what we did here is we looked at the channel quality, and we did it like here. You can do exactly the same thing if you, for example, fix instead the rate, and we'll do both of those. And so now the difference is we plot here the rate, and you would have curves like this, and you would look at how, okay, sorry, so this should be r minus c here, and you would look, it's exactly the same picture. Okay, so if you're either thinking of a constant rate code, and then you're thinking of scaling the channel parameter, or you're thinking of a fixed channel parameter and then scaling the rate, essentially these are the same points of view. So the scaling, if it applies, and I'm writing it down now for one form, would be that the postulate that if you're looking at this probability of block error as function of r and c, and if you now rescale, so these parameters here, such that this is a constant, okay, so you're looking at the curves at constant probability of error. This is a constant probability that you have here. You let n grow, but you're getting, as n grows, you're letting r grow closer and closer to c here, such that this is a constant, that this has a limit, okay? And if that indeed is true, then the two parameters of interest are the scaling parameter mu and the scaling function f. Now, typically, mathematically, we're talking about this, but in practice, you can also then, it turns out to be, it's often very, very useful, simply forget about this limit here, and simply instead of f of z, plug in here this function here, and then to say that the error probability roughly behaves like f of z. Okay, so to get actual curves, and we'll often plot these curves. Now, strictly speaking, you don't know then, or unless you have some extra statements, you don't know necessarily how much the error is for any given given n. You just know that as n becomes large, this will become small. So you don't necessarily know, for example, that there's uniform convergence. But again, somehow it turns out that in most problems you're looking at, that even for fairly small n, these are extremely good estimates. Okay, good. So now, if you want to, so one possible reference in the physics literature is this Privman, and as I said, it has a long history in statistical physics. Now, I'm also sometimes saying a little bit something on complexity, not really much. There's the obvious. Sometimes algorithms are exponential. Sometimes algorithms are polynomial time. Often, of course, we're interested in things that are linear. But even if things are linear, as we look at the scaling, what can happen is that constants blow up in front. Okay, so typically, we wouldn't be very surprised to see that at some systems, even if you have a linear complexity, maybe as you approach the threshold or the capacity, that as a function of this gap to this thing, some constants will blow up. Degrees will blow up, number of iterations will blow up, etc. OK, so let's first get started with block codes. We'll do this very quickly. Block codes, we know they achieve capacity. Let's look quickly at their exponent. So all the air exponent all the way up to capacity is strictly positive. Maybe one thing here is it's actually of a quadratic form here, so it goes down like a second order close to capacity. Why are there so many curves here? Well, it depends now exactly. Are you looking at the air exponent of the best code? Are you looking at an average code? Are you looking at an ensemble of linear codes? Or are you looking at the ensemble of, for example, of the Shannon ensemble, where you just pick all the code words IID? This doesn't make a difference here, but if you're further away from capacity, it depends a lot on the minimum distance, and then there are differences between these cases. Okay, we'll not really enter in this. There's some very nice. So of course, the first one that worked on this was Bob Gallagher, and there's a very nice review paper by Sasha Bark and Forney, fairly recent, where it's just 6 pages long, but it gives a very nice review of, if you want to know more about this approach. OK, now let's look at our first scaling. OK, so let's do a very simple, let's derive a very simple scaling law. Let's assume we had a perfect code. And what I mean with this is the fraction of erasures we have. There's some capital N in there, which is the block length. And let's assume that as long as we have as many bits received that are not erased, as there are degrees of freedom in there, I can decode perfectly, okay? But as soon as it's more, then clearly I cannot decode. So I have a complete step function. So the conditional probability of error, conditioned on the number of erasures, is either 0, and then it jumps to 1, okay? And let's assume for such a perfect code, how would things scale? Okay, easy exercise. Well, let's look at the distribution of number of erasures. They're just picked IID. They have a certain erasure. Every bit has an erasure probability epsilon. So in expectation, I get n epsilon errors. And then I simply look at the variance of this. And of course, I also know that by the central limit theorem, that this distribution around the mean, as long as I'm staying roughly square root of n away, will converge to Gaussian. So this will behave like a Gaussian. And so what will be the error probability? Well, it will be exactly probability that the number of erasures is larger than this threshold, right? So it will be exactly this part of the Gaussian tail here. And we know from basic communications courses that this can be expressed as a Q function. So this error probability will be the Q function, where we simply look at the distance here, okay, d, and then divide it by sigma. Okay, so this is exactly the expression. And then if we cancel out the sigma here, then voila, we have exactly our first scaling law here. Behaves exactly like this. So we have n. Now here, this is square root. So mu is equal to 2 here. So it's n to the 1 over 2 times the difference between, this is the threshold here, okay, 1 minus r, the difference between the threshold and the channel parameter. And then this is one of the scaling parameters here. So it has exactly the form that we wrote down here, where or the scaling function f of c is q of z over this parameter here, the channel parameter I have here. Okay, so now this is a perfect code. Now, how would a random code behave? Well, it's fairly easy to see a random code behaves essentially exactly like this. Why? Well, if you take an n by n random matrix, so I'm talking about now random linear block code, and I take an n by n matrix where I put the zeros and ones, in equally likely, and I ask what is the probability that the rank, that this has full rank. Okay, that's exactly the condition that you can decode, because for the erasure channel, decoding means you're solving a system of linear equations, and the question is, does the system of linear equation have full rank? Okay, so what is the probability that a system here has full rank? So n by n would mean that we're exactly working at the threshold here. Well, it's not very hard to see that this goes actually to, even for relatively small numbers, maybe n10, it's very, very close. So this actually doesn't go to 0, but this actually goes to a constant. So roughly with a 0.25% probability, if you take a full n by n matrix, it will actually have full rank. And even more, if you make it a little bit less tall than wide, so if you back off a little bit, you're having a few extra equations than you have unknowns in there, then this drops very, very quickly. Okay, so it drops by, if you have 1 less, it drops by a factor 2. If you have 2 less, it drops by a factor 2 to the 3. So if you have 4, it drops by a factor 2 to the 6, etc. Okay, so it drops very, very quickly. And so because of this, if we're going to the previous plot, this width here of for a random code is actually constant on an absolute scale, not on the scale. This is all normalized by n, but on a constant scale, this transition. Okay, if I'm saying this is probability 1 here, what's the probability here, let's say 6 away from 1 on an absolute scale. Okay, this might be 10 to the minus whatever 10. Okay, so this drops extremely rapidly, and because of that, since the distribution here is of an order square root of n, right, it's much, much larger, this is actually essentially exact. Okay, so you have a small little error term, but essentially that's it. Okay, so here we see our first scaling law. We take a random linear block code, we transmit over erasure channel, we do optimum decoding, we get exactly a scaling of the order here, and it behaves like, important is here that we have here mu is 2, so that we have square root, and when we have exactly this form here. Okay, now what happens in the more general case? Sergio already alluded to it a little bit yesterday. I'll talk in a second about the history. But in the general case, here is one result, and I didn't state any of the conditions. I just want to give you the flavor. So if I'm now not talking about the erasure channel, but I'm talking about the much more interesting case of a general map decoder, if A is kind of the largest size of a code that you can have of length n, such that it has a certain probability of error p, then we know that if n was very large, okay, and I want to transmit at some small error probability, well, we know that I should, if I take the log, that I have so many degrees of freedom here, okay, normalized by n, that c is the capacity. But the question is, how do I approach that? And so there's exactly a penalty term here. And again, the important part is that you have square root of n. This is what Yuli and Sergio termed the dispersion here. And this is written in a slightly different form, but it's the scaling of exactly the same form, where now the scaling function is essentially exactly this function here. Okay, so block length, the largest capacity, and that's the dispersion. Now, this has a very nice history. The first results along the line go back to Strassen somewhere in the 60s. It's kind of interesting. Strassen, I don't think he's very well known in our community, but he's actually an amazing guy. If any one of you maybe knows not the matrix completion, but the matrix multiplication problem. Matrix multiplication, you take two n by n matrices, and you multiply them, and it's obvious that the number of operations that you need should be n-third, right? Except that that's wrong, okay? So someone found, or Strassen was actually found out, that actually you need quite fewer, and the conjecture is that you actually only need n-squared operation, which is, the first time you think about it, saying it's obviously wrong. Okay, how can this possibly be? But he was the first guy that found an algorithm that can do better, and he had many contributions, and the best methods I think are also currently due to him. It's called the laser method, and I think right now the best exponent is you can do it in n to the 2.39 or something like that. Okay, so he had many, many nice contributions. And if you have in the last 2 years gone to any conference, I hope you have listened to either Yuli Polyansky or Sergio's talk, where they have many very nice results exactly on scaling of this form for various channels with memory, et cetera, et cetera. Okay, so this is exactly a scaling of this form. And so this tells us that what we should be hoping for, what we should be aiming for, is a performance like this: capacity minus something square root, and then hopefully, if we are lucky, we might get a parameter like this. Okay, so here are some of the references. I only put some up there for if anyone wants to look them up. Okay, now let's go to convolutional code. Who is this person? Peter Elias. Okay, so the inventor, of course, of convolutional codes. I'll be very quick for convolutional codes. I hope all of you have at some point seen a convolutional code. I just want to tell you what we could expect. So the first important result, that's due to Judkin and Viterbi, was that convolutional codes also achieve capacity. And not only do they achieve capacity, if you look at the air exponent, you remember for block codes, this was actually the second was of second order, but here you actually get a slope, so you get a much better exponent close to capacity here. Now, this was originally proved for what's called time-varying convolutional code. So these tabs at any point in time would switch according to some random process here. Now, more recently, Zigangirov in '85 and then Schulman and Feder have proven that for various actually time invariant codes, you also get the same result, although you get some slightly different exponents as you have up here. But the important thing is they achieve capacity. Now, how exactly do we compare block and convolutional codes? For block code, if you don't know anything and you want to decode it in map decoding, the best thing you can do, there's somewhat better schemes right now, but the best primitive scheme you can do, or let's say the most obvious scheme you can do, is simply list all the code words there are and compare one by one, right? So that's exponential complexity, and the complexity would be the number of code words, 2 to the n times r, right, where r is the rate. So that would be the complexity to do map decoding. So now, what is about convolutional coding? For convolutional coding, if you do optimum decoding, that's the Viterbi algorithm, and the Viterbi algorithm, let's assume everything is binary, would have complexity 2 to the number of memory elements you have, because that's the size of the trellis that you have at any point in time. And so you should compare the lengths. So the length, the effective length that typically people compare is that they take this what's called the constraint length, you divide by r, and then the complexity would be exactly, again, 2 to the r times this quantity here. Okay, so these would be the two quantities that you compare. Okay, now, so we know they achieve capacity. What about scaling? Here's the first open problem. As far as I know, nothing is known about scaling. Okay. In fact, I ask a little bit. For example, Dan Costello was very nice to answer. I think even in terms of simulations, when people like plots, I'm sure people have done other simulations, but even plots that are publicly available, I think more or less the best, or more or less almost as good as the best, are simulations that were done, I think, sometimes in the 60s by Heller and Jacobs, in which you have here the constraint length k. And so you have here the EB over N0. This is for a rate-and-a-half code. So you make, for example, a line here. That's what scaling asks us to do. Scaling asks us to look at a certain fixed probability of error. And now as the constraint length grows, we're asking how does this approach the threshold here. And what is the threshold here? Well, we know from the previous slide that the threshold is capacity. And since this is a rate-and-a-half code, it's binary input, the threshold would be roughly at 0.18 dB. So we are here very, very, very far away, right? Like 0 is, I don't know, somewhere here. Okay. So of course, from this data, it will be very difficult to say what the scaling is. But if you really wanted to compare, I think, block and convolutional codes in terms of complexity and performance, I think that would really be the most meaningful measure to see. We know for block codes how this works. Now let's see for convolutional codes. How fast do they actually approach this? How does the scaling work? And then I think this would be an even more meaningful comparison for practical scenarios where you really want to operate at a fixed probability of error to see which one is better, convolutional or block codes. Okay, so anyone have an appetite for this? This, I think, would be a very nice open problem. Okay, so here I give you some of the history. Elias introduced them, of course. There are many other decoding algorithms that I didn't talk about, particular sequential decoding, and you can ask the same types of questions for these types of decoders. Fano algorithm, the best known metric for a sequential decoder is the Fano metric. Then the whole history about how people found out that Viterbi decoding is actually optimum decoding. There's some other reference I think I missed. There was an important reference by Heller. And as overviews, there are, let's say, three. I'm sure many other ones, but let's say three of the classic ones is Viterbi, Lennon Costello, and Johansson and Tsigangerov. OK, so that's all I'm going to say about convolutional codes. Open question. If anyone is interested, I think it would be very nice to look at actually how these codes scale. OK, so now many years ago, when I somehow didn't know what I should do, I looked around a little bit, and I found a paper. OK, maybe it looks familiar. And so I browsed a little bit and looked around. And there's on some page, and Sergio yesterday, I think he went a little bit over the that's the page when we're talking about how the language can be modeled by higher, you start with a zero-OR process, etc. Okay, and so while browsing, I browsed around a little bit, and I happened to zoom in the part here, and I found something which I found surprising. Anyone? Like, I don't want to make it too, just look like here, OK, so let me show it to you, because you might not see it. OK, if I looked closely, look at that. OK, now, I don't want to overinterpret it. I'm not saying Shannon knew about LB, but OK. But, OK, if you think that's the end of the story, think again. OK, now, since this was many years ago, and that obviously inspired me to work on these codes. So I thought, now, I don't know. I thought, maybe let's have a look again. And now this one was harder, I must admit. I'm not sure if you know these kind of pictures, these 3D pictures where, they're just, in the picture is flat, but if you somehow don't concentrate, you gaze, you let somehow go, you gaze, and suddenly this picture pops up at you. Right, so it's kind of more of this type. So if you gaze a little bit more, perhaps you can find something else. Also, maybe another hint. You might know that there are these records that look completely, innocent, like whatever, Michel, my bad. Okay, and then you play it backwards. Okay, and suddenly, you find the true meaning. Ever seen have some experience? So yesterday evening, I was done with my slides. I said, OK, what I'm going to do? I need some inspiration. And anyone? Any takers? It's difficult, but you'll be surprised.
It starts with S. Yeah. Oh my God.
OK, the slides will be on it. Good. So now, let me talk about another hero of ours, and that's, of course, Bob Gallagher. And this is, of course, Beroux and Clavieux. Now, here's some cute pictures. OK, Bob at various stages. That's probably when he invented LDBC codes. I guess he did the air exponent. I don't know exactly. I tried also to find equivalent pictures for Beroux and the late Clavieux. But it's essentially impossible. And at first thought, how can this be? But then it was fairly clear. I mean, with physicists, you never know at exactly a certain point where they will be at a certain time, right? So it's very difficult to take some pictures. Good. So now, first, a couple of minutes. I hope you have all seen, in general, iterative coding and sparse graph codes. This is obviously not enough time to really introduce a lot here. So I'll just mention a few things so that some of the pictures will make sense. We have a set of variables. We construct a linear code by introducing constraints. Each of these constraints is a parity check, is a linear equation. So this says, for example, that bit x1, x4, and x8 have to sum up to 0. Everything is binary. And I now give many such constraints. And the point will be here that that compared to the previous ensembles we looked at, let's say block codes, which all have a representation like this, and also convolutional codes, will be that these nodes here will have very low degree. In a random code, you would expect them to have degree roughly n/2, but here they have fixed constant degree. And sometimes I will not really need this. There you can describe how many nodes have how much degree, and you can give a degree distribution for both sides. And so the code is defined as the set of all the solutions x, such that h times x is 0, where this H matrix here corresponds to this connection matrix here is sparse. And typically, we are not looking at one specific code, but we're looking at ensembles of codes. And so typically, we get the ensembles by picking these permutations here from the set of all possible permutations. OK, so now let me just mention 2 words about the analysis. I will be, again, very brief. I hope you all know that typically we analyze these sparse graph codes under one of the following algorithms, either a message passing algorithm in which I send messages along the edges of the graph back and forth in iterations. There are many other ones. There's something called the flipping algorithm. There's also something called linear programming decoder, for example, where Alex has worked on extensively. I'll stick right now with the message passing decoding algorithm, although you could ask the same kinds of question under any of the other decoding algorithms. And so typically, the first order of what we do, we're looking at first, how good are these codes? Okay, so the first question, if we want to, before we even talk about scaling, we need to first figure out, do these codes even have a threshold? Because it only makes sense to talk about scaling once we know that these codes have a threshold, and we'd be even more happy if the threshold turned out to be capacity or close to capacity. OK, so in order to know that, we're looking at larger and larger graphs. And then the typical picture is the following. I look at a very large graph. And to make it simple, think of the erasure channel. This is the erasure probability. Think of the following experiment. You take a very, very large code. You pick a random code word from this code. You transmit it over the channel. The channel inserts a random set of erasures according to an IID process with erasure probability epsilon. You take this code word. You put it into the decoder, which sends messages back and forth. The decoder, particularly for the binary erasure channel, will have a fixed termination point. So at some point, it will either have decoded everything or it will get stuck. And you simply record what is the erasure probability at the end that you get when the decoder is stuck. Okay, and so you plot that as a function of the channel parameter. You plot what is the parameter of the where do you get stuck. And clearly, it's not too surprising, of course, that if you make the erasure probability better, then this erasure probability should become, that you get at the end, should become also better. And if you did the experiment, you would find out, so these are certain points, that there will be some point here, somewhere between these 2 points, where suddenly if you do this for very, very large codes, you will find out that with very, very high probability, you actually decode, okay? Virtually every time you will do the decoding. So this point is exactly our threshold. So there's some threshold here that characterizes if we're operating over here, with high probability we can decode. If we're operating here, with high probability we'll get stuck. Okay, so we have found our threshold. Now the nice thing, and this analysis was done by Luby, Mitzenmacher, Spielmann, Chocolari, and Steeman. The nice thing is that, at least for the binary erasure channel, this description of the threshold is actually very, very nice and very explicit. And I can, particularly, this is now for a code what's called a 3-6 code, where all Theorem nodes have degree 3, and all check nodes have degree 6. It has, and this curve here has a very, very simple parametric description here. When x is the parameter, then what it's plotting is this parameter here. This is essentially the probability of bit erasure, not taking into account the received value itself. And this is, and if you, so essentially for every x, you're looking at the fixed point of this equation here, and then you're plotting that, for every epsilon, you're looking for fixed points of this x here, and then you're plotting epsilon of x versus this function here. And that's exactly the curve you get here. Okay, so that's the curve, yeah. So now, given that we have a very explicit characterization, let me skip this for now. Given that we have a very explicit characterization of the threshold, it is natural that the next question you can ask is whether or not you can make this threshold equal to capacity, because that's really what we would like to do. And in this beautiful paper here, again, but the same set of people here, they showed that indeed you can do this. Okay, so you can choose these degrees in a way, and in particular it's a sequence of degrees. There's no single sequence that achieves capacity, but there's a sequence of such degree distributions that achieve capacity. You can do this such that you give me an epsilon, and then you just need a little bit some overhead, 1 plus epsilon, and they also have a scaling here in terms of how, for example, the complexity grows. So for any epsilon, you just give me a little bit away from epsilon, you can find a code such that you have an overhead at most epsilon and that your error probability is at most epsilon. Okay, so so that's nice. So in terms of the threshold, we know now that at least for the erasure channel, we can achieve capacity. Now, for channel channels, it's unfortunately not so simple. We don't have a characterization, explicit one. We have to use some numerical computation to actually compute these thresholds. And in some work that Se-Young Chung, who was a student at MIT of Dave Forney, he basically used some techniques called dense evolution to optimize these thresholds. So there's some characterization again of the threshold. Once you have a characterization, you can again optimize the degree distributions. And you can ask, how should you choose these degrees in order to get as close as possible the threshold to the capacity? And you can again get very, very close, 0 point whatever, so many 0 dBs away from capacity theoretically. And then if you can actually run simulations, you see that you get very, very close. Okay, so you get close, but strictly speaking, we don't know yet that they achieve capacity. Okay, so now let's again ask our two questions. What do we know in terms of iterative sparse graph codes, in terms of both the error exponent and the scaling? Okay, the error exponent, I will be fairly brief. Error exponent is actually quite tricky, and so I didn't write down a lot here. So the way typically you prove anything that some codes can have error exponent, or that's possible to construct iterative graphs that have error exponent, is that the first thing is you prove that there's a concentration of the performance, and that's this statement here. What does this statement say? It says that if you're looking at, for a particular graph and a particular epsilon and for a particular number of iterations, you look at how this is a random variable here because it, let's say, it depends on the channel realization here. And you look at how does this performance compare to the average performance over the whole ensemble. Then you can show that, similar what Sergio was talking about yesterday about random codes, that not only there's some good codes in there, but essentially all the codes are good. Okay, most codes are within a small delta away from the performance. Okay, and this happens actually exponentially fast. Okay, and the way you prove this is by a very beautiful general technique. I think that's very useful, called the in computer science it's typically called the Azuma inequality. It was first proved in math in Höfting, and now sometimes people call it the Höfting-Azuma inequality. So now the point is like this. So typically the way then you try to prove that there are codes that have error exponent is then you say, OK, fine. So this means that I can essentially look at the expected value. And if it happens that I can show that this expected value, if I make n large, can become arbitrarily small if I do enough iterations. And if I can, for example, show that there's a code that has a fixed error correcting radius, meaning in the worst sense. So maybe this code, I know that this code can always correct some alpha times n errors, no matter what. Okay, if this fulfilled, then basically the idea is first prove that with exponential hyperbole, I fall within this small error correcting radius. And then once I'm there, I know for sure that I can't get stuck. Okay, and now the question is, what would guarantee us that we have such a behavior? Well, there are different conditions, but essentially all, or most of the conditions come down to looking at what's called the expansion of a graph. I'll tell you in a second what that is. And so typically what that means is that you need to look for a graph that has high expansion. And it turns out that if you take these regular graphs that we had before, and if you guarantee that the left degree is at least 5, that typically would apply. So codes with left degree larger than 5, they would have this large expansion, and then you could prove that they would have some error exponent. OK, now that's nice. The only problem is that typically the codes that you construct in practice, the one that have good thresholds, etc., do not have these large degrees. They do not fulfill it. And so typically all the codes that Jack told you that, for example, LABC codes are in magnetic recording things where they even need error probabilities of 10 to the minus 15. Nevertheless, these codes typically do not have error exponents. So these classes of codes do not have error exponents. And so that's typically not how to design it. But if you wanted it, that's how you would have to do it. And just in case you're curious what the expansion is, well, if you take a graph and you take a certain set of variable nodes, then simply look at all the neighbors that this variable node has. Okay? So let's assume the neighbors are those. This doesn't really correspond now to something. I pick some variable nodes and I look at all the checks that are connected, let's say, to these variable nodes. Let's presume that these are the checks I have. But how many could I have at most? Well, if this graph has, let's say, every node has degree, let's say, DL, right? Then at most, every of the variable nodes could be connected to DL check nodes. And if I'm lucky, there's no overlap. And so at most, I could have DL times the size of the set I started with, right? But I will not always be so lucky. Once in a while, there will be some overlaps. There will be neighbors that share, or certain variable nodes that share neighbors. And so the question is then, what is this largest, or what's the smallest ratio that this ratio can become? Okay, we know that it could be at most 1, but in general, it might be slightly less than 1. And if you go over all subsets of up to a certain size, then this minimum here is essentially the expansion. Now, it's fairly easy to see that the expansion of a regular graph can never be better than this DL minus 1 over D. So it can't really be 1. The best we can hope for is this. And why is this very easy to see? Let's look here at the computation graph that you have. So this is, let's say, a variable node you start with. So I'm picking now a particular set of variables. So this is a variable node I start with. It has DL checks. So far, so good. Now, each of these checks has, again, some variable here. But how many checks does this variable node neighbor to? Well, here, since one of the nodes already connects up here, this only connects to DL minus 1 extra check nodes here. Is that clear? So take now this set of variable nodes, all these variable nodes I have here, and the variable node in the middle as the set that we start with, and ask how many check nodes does it connect to. And essentially, since the most number of variable nodes are at the boundary, the ratio will be determined by the points at the boundary. And the points at the boundary, each of those, even if you have no overlap whatsoever, just given the structure, each of these variable nodes has only DL minus 1 extra check nodes. And that's exactly where this DL minus 1 comes from. Okay? So the best we can hope for regular graphs is that we get DL minus 1 over DL, so something slightly less than 1. And it turns out in order to have the expansion that's large enough for us to work, we need that this expansion is at least 3/4. So you can ask for which number does this work, and 5 is the first one for which it's strictly bigger than 3/4. Okay, so 4 would give me exactly 3/4, but I need something strictly bigger. So that's why we have this property. Now, one thing I didn't mention is that the remarkable property is here that this is an upper bound, but that for random codes or random graphs you pick, that with high probability, they have expansion indeed very close to this. Okay, so that's essentially all you need to know. We need large expansion. Random graphs have essentially the largest expansion that they can hope for, and we need expansion at least 3/4. And the best, the first one that fulfills this is degrees 5. Okay, so if we are willing to have very large left degrees, that's fine. But typically, we can't construct very good iterative codes in terms of thresholds. Okay, so now let's come to finite length scaling. So for finite length scaling, this is one of the cases where we actually indeed know something. Okay, we indeed know something precise. For the BC, we can actually prove a scaling result. And it has exactly, again, the same form, namely that I wrote it down now in this form here, namely that, again, this error probability here is given by, again, this is, again, the Q function of z over alpha, where this z has exactly, again, the same form as before. Namely, I have square root of n, and then I have epsilon, the threshold, minus the epsilon. And indeed, for this case, we can prove something slightly stronger. Namely, we can prove that this is a higher order approximation. There's in this expansion business, you can essentially, like in a Taylor series, you can give any number of terms in here. So this is even slightly more precise. And it turns out that these scaling parameters you can compute. Okay, so there's a web page or there's a simple formula. You plug in Mathematica, it's analytic. You simply plug this in. You get some numbers. What do you need? You need the threshold that you get from dense evolution, and you need the alpha and the beta. Again, this is something you can simply compute. You can plug in into a formula. And if you do this, then you can check how well this corresponds. Now, again, as I said, we do here always something illegal in some sense. What we do is we're not just looking at the limit here, but we're actually using this now as an expression or an estimate for a finite length. Okay, so I pick now a finite length. For example, that's length something like 350. And I plug in now the expression. So I plug in exactly this. I forget about this error term here. And I plug in this expression here with the alpha and beta and epsilon computed according to this program for a particular code. That's a particular code here. This is again for the binary ratio channel. I plug in, have the rate. I can plug in what the threshold is. And these would be my estimates for the error probability, the block error probability curves. And we happen to be, and this happens very often, but to some degree it's luck. We happen to be lucky because if you look at up here, you can, for this case, compute these curves exactly. They happen to be exactly on top. Okay, I don't claim that this is in general true, but there is a general phenomena that these estimates often are very, very good already for small lengths, even though there's no guarantee a priori in the way they were derived that this should be true. There's an error term, and a priori, unless you get a good handle on the constants here, you wouldn't really be able to say how good this estimate should be. Okay, so given that we can at least empirically predict things, you can see why scaling laws would be useful, because now you might think about optimizing things, right? You're saying, okay, so if I know for a certain degree distribution how these things really behave for a particular length, then let me try to optimize this, right? So let me pick, for example, a length. I guess in this case it's something like 4,000. And let's say, do a requirement like in a filter design. I say that the block error probability has to be less 10 to the minus 4, at least up to whatever, 0.5 or what this value is. Okay? And let me now try to, for every degree distribution, I compute what the prediction is. That's the prediction. And now I'm trying to optimize. And so one thing that I haven't told you before is that the scaling law applies to large-scale failures. So it applies to whether or not the decoder gets stuck at some constant times n fraction of the erasures. In addition, for LWC codes, since often or most of the time they don't have error floors, they don't have an error exponent, you can also have error floors. And that's an extremely important topic, but something that I completely will skip under the rug. So in addition, you also need to worry about error floor, and some topic that I know several of you are working on. And so there's, in addition, some estimate about the error floor. Okay, so what you would do now is you take your favorite optimization program, you plug this through, and you would see, given that you have explicit expressions, it's fairly easy to optimize. And you would try to, of course, see, and you would see that hopefully there's some progress and what fraction of capacity, let's say, you could achieve. And I guess if we had at that point been a little bit smarter or known about finite length scaling in general, you should actually compare this probably for the actual length that you're operating and not against, let's say, capacity. Okay, so that's for the BC. Now, after you do this, you run simulation, and hopefully everything work out so that indeed the simulations predict. But so that's essentially the program. Now, what do we know in the general case? In a general case, it's more complicated. There's no proof that the scaling law is correct, different than from the BC. But what you can do is you can postulate that a scaling of the same form is true. And given this postulate, you can develop techniques to actually compute the parameters. So we have parameters according to dense evolution, etc., or programs that actually compute these scaling parameters, postulating that there is a scaling of this form. And this is, for example, the BSC. This is the Gaussian. And again, for various lengths and various degree distribution. And so actually, degree distribution and channel is already given. And again, you see the various lengths, and you see the predictions, and you see the actual simulation results. Okay, so this might, again, be a useful tool for design. But again, a very nice, important open problem is proof that indeed such a scaling law applies also in the general case. Okay, now let me now show you why, and we'll get back to it later on when we talk about polar codes, why scaling can be a very nice predictor of something that we also observe. So let's look at the gap to threshold versus the length. So what we're thinking about the following: we have a scaling law of this form. And so this is the form of the scaling. And now what we know is that by fixing z, we're fixing the error probability, right? Because remember, the error probability estimate is the scaling function of z, right? And so so let's assume I fix the z here. And let me assume now I want to see the relationship between the r, the c, and the n. Okay? So let me call the difference between the c and the r the gap. Okay, so it's the additive gap to capacity. And so then I have, and now let me solve for n. Then we see that n behaves like z over delta to the mu power, right? And so now what does this mean? This means if in our case mu is 2, right? So for LDBC codes it's mu. This means that if I want to close in all these curves that you have seen before, and if I want to get, I'll show you in a second example, if I want to get close the gap by a factor 2, I want to get a factor 2 closer to capacity, maybe I have 1 dB gap, I want to have only half a dB gap, and I ask how large does the actual thing have to be, then we'll see that actually the, so let's look at the curves, let's hone into this, and then what we will see is that, or what we see from the formulas here is of course that if I make this a factor half here, and I take the second power, that this would mean that I have to take the length and increase it by a factor 4. Okay? So halving the gap to capacity by a factor 2 means I have to increase the length by 4. And you can check this, right? So for example, all these elements here are by factors 2 the lengths. So pick a length here, okay? And so this is a length, this is factor 2, this is like factor length 4. And this is the threshold, and you can see indeed that these lies exactly in the middle between the two. Okay, so scaling, once you know even just the scaling, if you just know the scaling component, then you have a very, very quick way of predicting. If someone tells you, okay, so I have a code of a certain length, how much would I gain by, let's say, increasing the length by a factor 2, a factor 4, whatever factor, there's a very quick way of actually doing this. Okay, now what about complexity? Let me perhaps, how are we doing in time? I see. So complexity is a trickier issue because it depends a little bit how you think about the implementation. Do you want vanishing bit, block, etc., probability? Essentially, for the BC, things we know pretty well. So let me just maybe mention the strongest part. The strongest result we know is that if you want to achieve capacity with the BSC and you have delta being the gap to capacity, then and you want to do this with the standard LDBC codes, then the complexity will grow like log 1 over delta. And this 1 over delta comes from the fact, or the log 1 over delta comes from the fact that your degrees of the graph have to grow in order to achieve capacity. Okay? If you're willing to go to more elaborate structures, then you can do as well as actually with constant complexity. So you have only a constant number of operations per bit and achieve capacity. But this is a little bit cheating in terms of computer science, because what I'm assuming here is that simply, what I'm all assuming here is that I have to touch a constant number of edges. Okay, so that's correct, because I can do it with constant degree. But of course, if I have an n-length structure and I need to address the edges, okay, then if you actually need to implement it, you would assume that something should grow like log n, because I need to say where this edge is actually going. Okay, so this depends now on the exact computational model of what you consider complexity. It's a constant number of operations that you can get away with, but whether or not that means really constant complexity depends on let's say what you think is a reasonable computational model. Now for general channels, it's more complicated, and I'll think I actually skipped this. Okay, so here again, some very few references. Of course, much more has been done in this field. Again, of course, the two seminal parts here are Bob Gallagher's introduction of low-density parity-check codes, and then the invention of turbo codes. Some paper that deal with the analysis, some parts I talked about at the beginning. If you want to know more about error exponents, there's mostly David Burstein with his students. He has looked at error exponents also on the map decoding and many different things. Some papers, again, just some basic ones, and there's much more work and on finite length scaling. Complexity, there's a nice paper, old paper by McLeese and Kandahar. and then some parts of the overview. Okay, now some open questions. I think, probably if right now I was trying to solve something in this field, I think probably the most important problem still to solve from a practical point of view is to find a simpler design procedure. If you compare to classical codes like Reed-Solomon codes, BCH codes, people can go to pretty much any book, a web page. They know the parameters. You can look them up. You know what the field size should be. You know what the length, what the rate you can pick. You have good predictions on the error probability. Anyone, you don't need to study for 3 years coding in order to see these things, and the algorithms are well defined. There's a well-defined structure of how to implement them. For LDBC, it's still a little bit of an art. Error floors, there has been lots and very nice work on error floors, and I know several people in here have been working on this, but it's still a tricky issue. It's not like something that you can just give. It's not like there's a web page here, and pretty much for all classes of codes you might be interested, you just plug them in and you get a number out in a couple of minutes, okay? It's something that typically involves a lot of computation. I don't think there's general purpose programs around that you can just send to someone and has a nice user interface and would just predict this. So essentially, it takes probably many, many months for someone to start, looking up, deciding even on the structure. There are many, many structures from Turbo to ARA to coupled codes to all kinds of structures, even finding out. And even once you know all the performance, then you still need to worry about implementation. And typically implementation of these is very non-standard in the sense that it's very, very heavy on the communications part, namely the messages that you send, and not very heavy on the computations. And even modern, let's say, tools that would map a design, a VLSI design, into the actual hardware would typically have trouble doing the routing, etc. Okay, so anything I think that one could be done, even though we know lots about it, that to make that an easier thing. That the final aim would be have a web page, have something people with a moderate amount of knowledge in coding and communications can give their requirement, error floors, length, complexity, certain structures, and it would simply find a suitable code for you. I think this would go a long way. As Jacques said, there are many, many companies in magnetic recording and many other aims that want to implement these kind of codes, and I suspect that many of them spend a lot of time on essentially starting again from scratch, writing their own software, etc. Now, then of course there are many things you could do. For the general case, do they achieve capacity? You can ask about the kind of scaling results under all kinds of decoding algorithms, LP decoding, flipping algorithm, map decoding for channels, etc., etc. And also, so far when I talked about the scaling, so let's recall, for the optimum block codes here, the scaling with a constant mu is 2. For LDBC, you have exactly the same. But there's a slight difference, and we cheated a little bit. For block codes, we talked about scaling to capacity, right? Whereas for LDBC codes, we talked about scaling to the threshold of the code, right? And so the question there is still, okay, so if you actually want to compare this on an equal footing, you also need to maybe take a sequence of codes that approach capacity itself. And so the question is, do you still have this constant mu is equal to 2, right? When you take the sequence, or perhaps by getting closer and closer, you might get a divergence of the mu, and maybe the effective mu that you have is larger. And we'll see that in a second when we talk about polar codes after the break. And we'll see that large mu, and that happens, is not very good for us because it means we need very, very large block lengths. Okay? So I think there's some very, very nice issues in there. We'll take a break, and when we come back, we'll talk about polar codes.